Clamp-on ground tester is an acceptable method for testing the impedance of grounding systems for static discharge. It is important to note that the tester should be specifically designed for measuring the impedance of grounding systems. Clamp-on ground testers use the principle of electromagnetic induction to measure impedance. When the clamp is placed around a conductor, it generates a magnetic field. This magnetic field induces a voltage in the conductor, which in turn causes a current to flow to Earth. The tester measures the current flow and calculates the impedance based on the induced voltage and measured current. There is no specific impedance requirement for grounding systems for static discharge in the National Electrical Code or NFPA 77. However, a general guideline is to aim for an impedance of less than 2 ohms. This value ensures that static charges can be effectively discharged to ground. To test the impedance of a grounding system using a clamp-on ground tester, firstly, ensure that the grounding system is disconnected from any power sources. Secondly, identify the grounding conductor to be tested. Thirdly, place the clamp around the conductor, making sure that the jaws are closed securely. Fourthly, connect the tester to a voltmeter. Fifthly, apply a voltage to the grounding system using an appropriate power source. Sixthly, record the voltage reading on the voltmeter. Seventhly, calculate the impedance using the formula impedance equals voltage divided by current. The impedance should be within the acceptable range, typically less than 2 ohms. Do not clamp the tester around live conductors. Use the appropriate clamp size for the conductor being tested. Ensure that the tester is calibrated regularly. Test all grounding conductors in the system to ensure proper grounding. Grounding systems are crucial for electrical safety. They provide a path for fault current to return to the source, tripping the circuit breaker and preventing electrical shock. A low impedance ground is essential for the effective operation of this safety mechanism. Static electricity buildup can be a significant hazard in many industrial settings. When static electricity discharges, it can ignite flammable materials, damage sensitive electronic equipment, and cause discomfort or even injury to personnel. Grounding systems for static discharge provide a path for static charges to dissipate safely to ground, preventing these hazards. The principle of electromagnetic induction is fundamental to the operation of clamp-on ground testers. When an alternating current flows through a conductor, it creates a magnetic field around the conductor. Conversely, when a conductor is placed in a changing magnetic field, a voltage is induced in the conductor. Clamp-on ground testers use these principles to measure the impedance of grounding systems without disconnecting them. The tester induces a voltage in the grounding conductor and measures the resulting current flow. The impedance is then calculated using Ohm's law, which states that impedance equals voltage divided by current. While there is no specific impedance requirement for static discharge grounding systems in the National Electrical Code or NFPA 77, it is generally recommended to maintain an impedance of less than 2 ohms. This value is based on best practices and industry standards, and it ensures that static charges can be effectively dissipated to ground. A higher impedance value may indicate a problem with the grounding system, such as loose connections, corrosion, or damaged conductors. Regularly testing the impedance of grounding systems is essential for ensuring their effectiveness. This testing should be performed by qualified personnel using calibrated equipment. The testing frequency will depend on the specific application and environmental conditions, but it is generally recommended to test at least annually. When testing grounding systems, it is important to follow proper safety procedures. Firstly, always disconnect the grounding system from any power sources before testing. Secondly, use appropriate personal protective equipment, such as gloves and safety glasses. Thirdly, never clamp the tester around live conductors. Fourthly, ensure that the tester is properly calibrated and in good working condition. The clamp size is an important consideration when using a clamp-on ground tester. The clamp should be sized appropriately for the conductor being tested. If the clamp is too small, it may not make good contact with the conductor, resulting in inaccurate readings. If the clamp is too large, it may pick up interference from nearby conductors, also resulting in inaccurate readings. Calibration is essential for ensuring the accuracy of clamp-on-ground testers. Testers should be calibrated regularly by a qualified calibration laboratory. The calibration interval will depend on the manufacturer's recommendations and the frequency of use. Testing all grounding conductors in the system is important for ensuring proper grounding. This includes testing the grounding conductors for static discharge, as well as the grounding conductors for electrical equipment. Identifying the grounding conductor to be tested is crucial before placing the clamp around it. This ensures that the measurement is taken on the intended grounding path. The grounding conductor may be connected to a ground bar, building steel, or other grounding electrode. Ensuring secure closure of the clamp jaws around the conductor is essential for accurate measurements. This minimizes contact resistance and ensures a reliable connection for inducing voltage and measuring current flow. Connecting the tester to a voltmeter allows for precise voltage readings during the impedance calculation. The voltmeter should have appropriate accuracy and resolution for the measurement range. Applying a voltage to the grounding system using an appropriate power source creates the necessary current flow for impedance calculation. The power source should be selected based on the tester's specifications and the grounding system's characteristics. Recording the voltage reading on the voltmeter provides the data needed to calculate the impedance. The voltage reading should be stable and accurate for reliable impedance measurement. Calculating the impedance using the formula impedance equals voltage divided by current determines the overall resistance to current flow in the grounding system. This value should be compared to the acceptable range to assess the grounding system's effectiveness. Ensuring the impedance is within the acceptable range confirms that the grounding system can effectively dissipate static charges and provide a safe path for fault current. Values exceeding the acceptable range may indicate issues requiring further investigation and corrective action. Static electricity is generated by the contact and separation of materials. When two materials come into contact, electrons can be transferred from one material to the other. When the materials are separated, one material will have an excess of electrons, resulting in a negative charge, while the other material will have a deficiency of electrons, resulting in a positive charge. If these charges are not dissipated, they can build up to high voltages, which can then discharge, creating a spark. The amount of static electricity that is generated depends on several factors, including the materials involved, the speed of separation, the pressure of contact, and the humidity of the air. Some materials, such as nylon and polyester, are more prone to generating static electricity than others. Higher speeds of separation and higher pressures of contact also tend to generate more static electricity. Low humidity also increases the likelihood of static electricity buildup, as dry air is a poor conductor of electricity. In industrial settings, static electricity can be a significant hazard. For example, in the printing industry, static electricity can cause paper to stick together, making it difficult to feed through the printing press. In the textile industry, static electricity can cause fibers to cling to machinery, disrupting the manufacturing process. In the electronics industry, static electricity can damage sensitive electronic components, leading to product failure. To prevent static electricity buildup, it is important to ground all conductive materials in the workplace. This includes machinery, equipment, and even personnel. Grounding provides a path for static charges to dissipate safely to ground, preventing them from building up to high voltages. In addition to grounding, other measures can be taken to reduce static electricity buildup. These include increasing the humidity of the air, using static dissipative materials, and applying anti-static sprays. Static dissipative materials are materials that allow static charges to flow through them slowly, preventing them from building up to high voltages. Anti-static sprays are chemicals that reduce the surface resistivity of materials, making them less likely to generate static electricity. The NEC covers grounding and bonding requirements in Article 250. This article provides detailed requirements for grounding electrical systems and equipment to ensure electrical safety. NFPA 77, Recommended Practice on Static Electricity, provides guidance on identifying and controlling static electricity hazards. This document covers topics such as static electricity generation, measurement, and control techniques. Proper grounding and bonding are essential for electrical safety and for preventing static electricity hazards. By following the guidelines in the NEC and NFPA 77, businesses can create a safer working environment for their employees and protect their equipment from damage. The frequency of testing grounding systems should be determined based on a risk assessment. Factors to consider include the type of industry, the materials being handled, the environmental conditions, and the sensitivity of the equipment. In some cases, more frequent testing may be required, such as in areas where flammable materials are present or where sensitive electronic equipment is used. Records of all grounding system tests should be maintained. These records should include the date of the test, the location of the test results, and the name of the person who performed the test. Maintaining accurate records is important for tracking the performance of the grounding system and for identifying any potential problems. Regular inspections of grounding systems should also be conducted. These inspections should include a visual examination of the grounding conductors, connections, and electrodes. Any signs of damage or corrosion should be addressed promptly. Proper grounding and bonding are essential for electrical safety and for preventing static electricity hazards. By following the guidelines in the NEC and NFPA 77, and by implementing a comprehensive grounding maintenance program, businesses can create a safer working environment for their employees and protect their equipment from damage. The 2 ohms value is a generally accepted benchmark for grounding impedance, although it is not explicitly mandated for static discharge in the NEC or NFPA 77. Achieving this level of impedance helps ensure effective dissipation of static charges. If the measured impedance exceeds 2 ohms, it indicates a potential issue with the grounding system that requires further investigation. This could include loose connections, corrosion, or damaged conductors. Addressing these issues will lower the impedance and improve the effectiveness of the grounding system. The type of power source used to apply voltage to the grounding system during testing should be appropriate for the tester's specifications. It is important to consult the manufacturer's instructions for the clamp-on ground tester to determine the correct voltage level and waveform. Using an incorrect power source can damage the tester or provide inaccurate readings. The voltmeter used to measure the voltage should have sufficient accuracy and resolution to provide reliable readings. A digital voltmeter with a high input impedance is generally recommended. The voltmeter should be calibrated regularly to ensure its accuracy. Regular maintenance of grounding systems is crucial for ensuring their continued effectiveness. This includes inspecting the grounding conductors and connections for signs of corrosion or damage, tightening any loose connections, and replacing any damaged components. A well-maintained grounding system will provide a low impedance path for fault current and static charges, protecting personnel and equipment from electrical hazards. Clamp-on ground testers are a valuable tool for evaluating the effectiveness of grounding systems. By understanding the theory behind these testers and following proper testing procedures, qualified personnel can ensure that grounding systems are functioning properly and providing adequate protection. It is important to emphasize that clamp-on ground testers are not a substitute for a complete grounding system inspection. A thorough inspection should include a visual examination of all grounding components, as well as testing of the grounding electrode resistance. However, clamp-on ground testers can be a useful tool for quickly and easily assessing the impedance of grounding conductors. When using a clamp-on ground tester, it is important to follow all safety precautions. Never clamp the tester around live conductors. Always wear appropriate personal protective equipment, such as gloves and safety glasses. Ensure that the tester is properly calibrated and in good working condition. By following these safety precautions, you can minimize the risk of electrical shock and ensure accurate test results. In addition to testing the impedance of grounding conductors, clamp-on ground testers can also be used to test the continuity of grounding systems. Continuity testing verifies that there is a continuous path from the equipment being grounded to the grounding electrode. This is important for ensuring that fault current can flow back to the source, tripping the circuit breaker and preventing electrical shock. To perform a continuity test, simply clamp the tester around the grounding conductor and measure the resistance. The resistance should be very low, typically less than 1 ohm. A high resistance reading indicates a break in the grounding path, which should be investigated and repaired. Clamp-on ground testers are a versatile tool that can be used for a variety of grounding system testing applications. By understanding the theory behind these testers and following proper testing procedures, qualified personnel can ensure that grounding systems are functioning properly and providing adequate protection. The information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or engineer before performing any electrical work.